Hello all, and welcome to this video where we look at exponential equations, and more particular the index laws that help us solve them. Now, a couple of things I want to get off the bat straight away is around what's required in the study design and how this gets assessed. Now, part of the study design is there's a dot point in the key knowledge section that says index laws and log laws. It's key knowledge you need to know. You just need to know your index laws, you need to know your log laws. And then in the key skills, it says apply algebraic, logarithmic, and circular function properties to the simplification of expressions and the solutions of equations. So that's where the knowledge of index laws and log laws comes in, or is generally assessed, is in that point where you're just using index laws and log laws to solve an equation. Now, it varies how they assess it, but and I guess our big care is in the Tech Free exam, because Tech Active, when we're solving equations, a lot of time we can use our calculator to help speed that process up. But in the Tech Free, as I'll talk about later, generally doesn't come up as purely just a solve an index equation or just solve a log law anymore. It's part of some other bigger question. So while it is, you need to know it, and it's stated there in study design, a lot of time it's not assessed purely by itself in a nice simple 1-mark question. It just is an assumed skill that will have to be used at some stage. So yeah, it's one of the, we've had a lot of fundamentals, but this is another one. So let's get straight in. There's a refresher on the index laws. It's in the bottom of the slide. Down here, and the main thing that comes down to when we try and solve exponential equations without using an inverse, so the inverse of an exponential is a logarithm, so when we try and solve without using a log, or the process of logarithms, we're just trying to make the base the same. This is what this up here is talking about, the one-to-one property of exponential equations. If we can make the bases exactly the same on the left and right hand sides of the equations, we effectively get to ignore them, and we just deal with solving the exponents, because if the bases are the same, then for that equation to be true, then the two exponents must also be the same, so we can just then start dealing with whatever the exponents are. So let's jump straight in and have a look at some examples. So we've got 5 to the negative x equals 625. Straight away the 5 is a giveaway to what we should make the base. So we get 5 to the negative x is equal to 5 to the power of something that gives us 625. Now 5 squared is 25, times by another 5 is 125, that's 3, so then to the power of 4, so 5 to the power of 4. Now we've got two equations where the bases are the same. We can just now, if the base is the same, therefore the exponents must be the same, so we can then say that negative x must be equal to 4, so we get x is equal to negative 4. So that's how we approach that one. Same with b. We can see 2, 4, and 32. All those hopefully are in your mind that we can actually write those as a power of base 2. So we're going to get 2 to the power of x minus 1 times by 2 squared, that's what we can change the 4 into, 2x plus 1 is equal to 2 to the power of, is it 5? 2 is 4, then 8, and then 16, yeah, 5. So 2 to the power of 5. Okay, so we have that. Now with this 2 to the power of 2, all times all to the power of 2x plus 1, if we go back and look at this index law here, we can multiply those through, so we now get 2x minus 1 times by 2 to the power of, multiply that 2, there's lots of 2's, but I'm going to multiply that 2 by all of those terms, so we're going to get 4x plus 2 is equal to the power of 5. And now, next step, if we go back again, we can see if we have two exponents multiplied together that have the same base, just like here, we can just add those exponents. So we can now simplify this into 2 to the power of x minus 1 is the first one. Add the second exponent is equal to 2 to the 5. And now we have two bases that are exactly the same. And we can let the two indices, exponents, equal each other. So we're going to get x minus 1 plus, it should be 4x. 4x plus 2 is equal to 5. So let's simplify this. So we've got 5x plus 1 is equal to 5. 5x is equal to 4. So we get x is equal to 4/5. Yeah, and that's that. Do I have one coming up? No, that's a hidden quadratic. We'll come to it up. No, that won't be there either. It's come up before in the exam, and there's a lot of these style gotchas in the textbook questions where you have to... Actually, no, it doesn't apply for exponents. It's in logs. It's if we have a coefficient out the front, then you have to do some work with that in logs. But let's have a look at the other style of exponential equation that we might be asked to solve, which is effectively a hidden quadratic. So we have a look at this one. We have 9 to the power of x minus 4, which is the coefficient. 3 to the power of x plus 3 is equal to 0. Now there's a couple of giveaways that this is a hidden quadratic. One is equal to 0, but sometimes like this could have been equal to -3, but equals to 0 because that's what we let polynomials equal to then solve. The other is that it has a coefficient of the exponent. That also sort of screams that there might be a hidden quadratic. And then lastly, as we'll see, this 9 to the power of x, we can simplify it to 3 squared, which we can then rearrange to 3 to the power of x all squared. So there's three things that combine to help us show that this is hidden quadratic. One, we can turn to one of the powers into being squared. Another one is that one of the exponents has a coefficient, and then the whole thing is equal to 0. So we can see if we simplify that 9 to the power of x, as I said, to 3 to the power of x all squared here, we can now let 3 to the power of x equal to a. We could do x as well, but we don't want to use the same variable. But if we let 3 to the power of x equal to a, we can just replace 3 to the power of x with a. We can replace 3 to the power of x is a. And now we've got a quadratic in terms of a. We can ignore all the exponents for now, and we just think of its normal quadratic. We can solve using, or factorize using inspection. We can see that a is equal to -1, whereas a is equal to 3. Once we've done all our quadratic skills, we can substitute this back in here because we want to figure out what x was as our problem. So we've got 3 to the power of x is equal to 1, or we've got 3 to the power of x is equal to 3, and then we just solve. So let's work through this as a worked example. Might hopefully clarify this. Okay. It's clearly an exponential equation which we've been asked to solve. Can we make all the bases the same? Well, we've got a 2, trying to make 24 as power base 2, we're going to end up with a fractional exponent. That's going to be pretty hard. So let's then look instead, is this the other form, which is a hidden quadratic? Well, I have 2 to the power of 2, so there's a square in there. I have some coefficients in there, and the whole thing's equal to 0. So this to me screams hidden quadratic. So I'm going to first rewrite this as 3 by 2 to the 3 to the power of 2 to the power of x, and then bring that 2 up to the top, so it's much more obvious that it's a square. Minus 18, 2 to the power of x plus 24 is equal to 0. Okay, now I can do my trick of let whatever this exponent in here is, I can let that equal to a. And I can rewrite my equation as 3a squared minus 18a plus 24 is equal to 0. And now I've just got a quadratic that I need to factorize and solve. So we just go through our factorization tree or pipeline process that we want to use. And what's the first thing that we always try and do when we're factorizing any problem is just take out a common factor. We'll make, instead of having to do the cross method, will make our life a lot easier. So we take 3 out as a common factor. 6a plus 8 is equal to 0. We can divide both sides by 3, so we're now left with a squared minus 6a plus 8 is equal to 0. And we can now just, because we took the common factor out, we can now just factorize via using inspection. So multiply to give me 8, add to give me negative 6, that's going to be negative 2 and negative 4. Therefore I get a is equal to 2 or a is equal to 4. Now I'm not done. I need to solve for x. That's what my initial problem was in terms of. So I'm going to use this bit here, substitute it back in for a to be able to solve. So I now get 2 to the power of x is 2, and I get 2 to the power of x is 4. So in this case we can see x is equal to 1, or we also get x is equal to 2. So we have 2 solutions to this exponential equation. Here's an exam style question from a 2014 methods exam. Now, like I said, it's a little bit rarer now for just a straight out solve this exponential to be asked, especially in a tech free. Sometimes it's there, but more often it's a log, or it pops up in the tech active, and then you can just use your CAS. But we will go over it quickly because you'll see on the next slide. So this is the more straightforward one. We have no coefficients, so we're just going to try and make the bases be the same. So we get 2 to the 3x minus 3 is equal to 2 to the power of 3. That's what we can change 8 into, to 2 minus x. We can now multiply the 3 by both of those terms to expand that out, so we get 6 minus 3x. And now we've got this written in with 2 of the same bases equal to each other. It implies that the exponents have to be the same, so we get 3x minus 3 needs to be equal to 6 minus 3x. Bring 3x on the right hand side over, add 3 to both sides as well, so we get 6x is equal to 9, so we get x is equal to 9 on 6, which we can simplify to just 3 on 2. Okay, so that's that one. 13 minutes, we've only got one slide left. Now I said at the very start, and just on this slide as well, it's a little bit more uncommon for this style of problem to be asked, but you certainly have to be able to use, as I said, the study design says, apply algebraic, logarithmic, and circular function properties to simplify expressions and get their solutions to equations. Now, it doesn't say what type of equation it is. It could be given like this, but where it's popped up more commonly in the last 2-3 years is as part of a probability question. Now, it doesn't, this first bit here, the question doesn't have that in it. You have to do some probability stuff where you end up getting something that looks like this, and then, and it has all this other probability thing, and then it says, and give your answer in the form of a, b to the power of n, where a and b are positive rational numbers, and n is a, oh, and I've made a mistake, I forgot to delete this out, that 1 shouldn't be there, it should just be 5 on 6. Where a and b are positive rational numbers and n is a positive integer. So what is a rational number? A rational number can be a whole number, an integer, or a fraction, and that's the fact it says rational implies that a and b are going to be a fraction, and then n is a positive integer, so to the power of a positive integer. So we have to use exponential or index laws to be able to simplify this problem. This was in the Tech Free one in 2019. So how do we go about this? What we need to do is start to build this into the form of, because we've got an addition, and we're not solving, we're just simplifying. Because we've got an addition, we need to get, think of converting this where the exponent, so the 5 over 6 to the power of 11 and the 5 over 6 to the power of 12, we need to convert those so they're the same, so we can add two like terms together. So think of, we can add 3x plus 5x together, but we can't add 3a plus 4x because the a and the x, they're different. They're not like terms. We can't add them together, and there's no plus sign in this simplified form. So up here, we need to somehow get this bit and this bit, and also this 1 over 6 on 1. We need to turn those into the same b. It's effectively the b with the same power to be able to then combine them. Now, that's a lot of words, and you still might be confused what I mean by that. So let me just go ahead and show you what that looks like. How we're going to simplify this. So I'm going to leave the 5 on 6 to the 12 the same at the moment. I'm going to work on trying this right term, break it, simplify it a bit. Plus 12, and to the power of 1 makes life nice and easy for us. 1 on 6 to the power of 1 is just 1 on 6, okay, which we can then simplify to 12 on 6. We can write this as 12. Let me show full working out. Because we're just multiplying, we can write it in any order. I've left the 5 to the power of 11 there. We can rewrite it like that. So we now just got 12 times by 1 on 6, which we can also write as 12 on 6, 5 on 6 to the power of 11, okay, is equal to 5 on 6 to the 12 plus 12 on 6. Actually, I'm just going to leave it like that. I'm going to leave it as 12 on 6. We could simplify it to 2, but I'm going to leave it at 12 on 6, and you're going to see why in a second. So we've now got 5 on 6 to the power of 11 over here. So our base is the same, and we can effectively think as the 12 on 6 is our coefficient. So we've got 12 on 6. Let me just write it like this. We've got 12 on 6x, where x is 5 over 6 to the power of 11. The problem is our other term, we've got currently 5 on 6 to the power of 12, which is a little bit different. So how do I convert this 5 on 6 to the power of 12 to be 5 on 6 to the power of 11 with something in front of it? Well, this is where we have to use our index laws. We can change that to 5 on 6 to the power of 1 times by 5 on 6 to the power of 11. Because the 1 plus the 11 gives me the 12, plus 12 on 6, 5 on 6 to the 11. Now, the 5 on 6 to the power of 1 is just 5 on 6. 5 on 6 to the power of 11 plus 12 on 6 times by 5 on 6 to the power of 11. So we've now got, again, if I use my sort of analogy of like terms, we've got 5 on 6 x plus 12 on 6 x, where our x, what it is, just the 5 on 6 to the power of 11. So we can now combine these two because they are like terms. So we just get 5 on 6 plus the 12 on 6 is equal to 17 on 6 to the 5 on 6 to the 11. Okay. And we've now written in that form where we have a, so think of it as our coefficient, b is base, okay, and both of those are rational, they're both fractions, and then we have index, which is 11, and it is an integer, as it said there. And that's that problem. Now, as I've got here, that bit of the working out was probably worth half a mark on that exam. There was a lot of probability stuff beforehand, coming up with the binomial distribution, then simplifying into or changing it. You changed your perspective on it, and then you had to generate these equations and then add them, or these expressions and then add them together. So there's a lot of work just before this bit, and then this bit was, like the study design said, it's just knowing index and exponent laws to simplify. So yeah, what I'm trying to get at, index or exponent work is a fundamental. It's unlikely that it's going to be assessed purely just by itself as a single question. It is much, much more likely that it's just going to be assumed knowledge as part of other questions that may impede you either later on in the question like this, or unfortunately it might be something that you need to do right at the start of the question to be able to then do other work, which is just the way the cookie crumbles. As always, if you have any questions, please ask. See ya.